Yeah, hello. So we're going to continue in our exploration, and we've done enough. We did a bit of prerequisites, part one. So if you wanna get some background enough to think about Cayley's theorem, please check that out. And then we did a previous video introducing or motivating Cayley's theorem, and now we get into the meat of the theorem, trying to prove it. And in this video we're going to prove Cayley's theorem. Prove Cayley's theorem. Right. So, and what is Cayley's theorem? Well, the Cayley's theorem just is straightforward. It says that suppose G is a group, right? So I give you some group, and by the way, the group has to be finite. So I'm going to add that. Right. So suppose G is a finite group, then we're saying that G is isomorphic, the same as a subgroup H of the symmetric group Sn. So let's now proceed to prove this idea. And of course, notice once we prove Cayley's theorem, what we'll really be saying is that every group is isomorphic to Sn for some n. So really, if we would have proved that all finite groups, not every group, but all finite groups, which would mean that basically if you study Sn, the symmetric group, you're basically studying all finite groups. That's a pretty powerful unification if you think about it. So basically, another way to think about it is it's saying that all finite groups are really just the symmetric group in disguise. Alright, whichever one floats your boat. Hopefully all of them. Alright, so let's actually proceed to prove this. So how are we going to prove that G is isomorphic to some subgroup of Sn? Okay. So that's a correct question. How do you prove that? In particular, to explore here, we need to explore to ask the general question. If we have G and H as groups, how do we show that a group G is isomorphic to some group H? What's the methodology for that? Okay. And one way to do it is just to produce what is called an isomorphism. Right? That is, and we tackled that in the prerequisite. So you're going to get, it's going to be some function. If you can produce a function from the group to the other group H that you're looking at, and you have that phi is a homomorphism, right? You can prove that phi is a homomorphism, which means that basically for any G1, G2 elements of G, if you can prove that phi of G1 and G2 are elements of G, they all come from G. If you can prove that phi of G1, G2 actually equals to phi of G1 times phi of G2, right? And of course we're assuming phi is a function. If you can prove this, then really what we're saying is that phi is a homomorphism. And then you need to prove one more thing. You'd have to prove that phi, the homomorphism, is also a bijection. From G to H. Once we do this, once we find a bijective homomorphism or an isomorphism. A bijective homomorphism is called an isomorphism. Let's write it here. Isomorphism. Once we find an isomorphism between G and H, then we'll have shown that G is isomorphic to H. That's one way to prove that two groups are isomorphic. So how can we apply this strategy to our particular problem here of showing that any group is isomorphic to some subgroup of Sn? Well, so in particular, the tactic we're going to use is this, right? A little sneaky, but so what we're going to do is we're going to start with a group G. We're going to produce an isomorphism phi from the group G to the symmetric group on G elements. This just means order of G. So that means, for example, if G has G has 3 elements in it, let's say 1, 2, 3. Actually, I don't want to use the labels 1, 2, 3. So, for example, right, we need to be clear on notation here. So we're saying, for example, let's say G equals to G1, G2. Okay, I'll put it this way: G2, G3, and G4. Let's say that's what G equals to. Then the order of G is just, or the size of G is how many elements are in G. We know that there are 4 of them. So here what would mean is by the symmetric group on the cardinality or the size of G is just going to be the symmetric group on 4 elements, otherwise known as S4. So really what we're talking about here is S on the cardinality of G is just look at G, count, it's finite, remember, right? Count how many elements are in G, and then we're looking at the symmetric group on that number of elements. Right, so what we're going to do is we're going to find a homomorphism from the group G to the symmetric group on cardinality of G elements, or I'm just going to call them G elements now. We're going to find that homomorphism, and in particular what we're going to show is that phi of G, at least that's our tentative strategy. It may change in the process of this video, who knows, but what we're going to show is that phi of G, which is the image of G, is actually isomorphic. Phi of G is actually isomorphic to G. That is, will produce an isomorphism between G and phi of G. Phi of G is the image of G. Notice that phi is a map from G to the symmetric group on G elements. So it means that the image of G is some subset of the symmetric group. So why is this, how does this help us solve the issue? Now remember that in the prerequisite video, that's part 1 of this series, we saw that phi of G, if phi is a homomorphism, then phi of G is a group. Right? So what that would mean is that, and we also know that phi of G is a subset, right? Because phi moves from G to the symmetric group on G elements, to S on G. So the symmetric group on G elements. So what that means is that phi of G is a subset of the symmetric group on G elements. So phi of G is a subset of the symmetric group on G elements. And the conclusion we're able to draw from that, if phi of G is a group and phi of G is a subset of S of G, well, that means that phi of G then must be a subgroup, right? A subset of a group that's also a group is a subgroup. So phi of G must be a subgroup of the symmetric group on G elements, right? So, but now if we are producing an isomorphism, right? So we're saying if we can produce an isomorphism, let's call it, do I even want to go this route? Sure. So if we now consider phi from the group G to phi of G, right? Just, that is, we look at, we're doing the same G from the group, but we're ignoring things that phi never hits, that are not in the codomain of phi. Right, so if we consider instead phi from the group to this other group, right? Remember that we already said that if phi is a homomorphism, phi of G is also a homomorphism. So if we consider this phi from G just to the image of G, well, that's good. We're going to prove that that's an isomorphism. Once we prove that this is an isomorphism, then we'll be saying that G is isomorphic to phi of G, but phi of G is a subgroup of the symmetric group on G elements. So that would mean that then G must be isomorphic to a subgroup of the symmetric group on G elements. So that's the overall strategy. Seems really convoluted, but let's get into it. Right? So let's actually dig in here. So notice something, right? So for instance, as we noted before, let's start with the group G. Okay, so G is a group, is a finite group, so we can write it like this: G1, G2, blah 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 up to Gn. Okay, so one thing we note here is that if you get some element in the group, let's say some Gi, okay, and you multiply it by big G right there. I don't know if we actually need to label them G1, G2. Okay, let's just label them that way. But if you get some Gi and multiply it by G, well, that just means that Gi multiplied Gig, let me maybe write that out carefully. It's just the same as Gi left multiplied by G1, Gi left multiplied by G2. It's exactly what you think it is. Gi left multiplied by G3. All of this Gi left multiplied by Gn. So notice if G is a group, then Gi times G1 is going to be an element of the group, right? Because G is a group and groups are closed under operation of multiplication. So under the operation of the group. So Gi times G1 is a group element. Gi times G2 is a group element. Gi times G3 is a group element. Gi times Gn is also a group element. Okay, we know that to be true because G is a group and again by closure. So what we have here is then that every element in Gig is a group, is an element of G. But what we are wondering is Gig a permutation of G? Right, that's the question we're asking ourselves. And we'll see how this connects to the overall proof. But is Gig really a permutation of G? Is the question. What would proving that if I have some sigma and I'm saying that sigma is a permutation of the elements of G, right? I'm going to write is a permutation of G. If I wanted to prove that sigma is a permutation of G, how would I prove that is the question. Right? Think about it. How would we prove that something is a permutation of a group, for instance? The way to do it would be to show that one way to do it, and we don't know, maybe there are others. One way to do it is to show that, first of all, every element, for example, in the permutation is an element of the group, right? So if sigma is permuting the elements G1, G2, G3, or if sigma is permuting the elements 1, 2, 3 or whatever, then 1, 2, and 3 better be elements of the group. Because if you're not permuting elements of the group, how the heck can you be a permutation of the group? Right? So one thing is that to check is that one sigma is really, whatever the permutation is first of all the elements it's permuting better be elements of the group. And in particular, another thing to check is that the number of elements it's permuting is exactly the same number of elements in the group. And also another thing, so now we're saying the number of elements being permuted is exactly the number of elements in the group. And we also know that we're saying that we want to show that all the elements in the group, all the elements being permuted are elements of the group, right? But that's not enough because, okay, so what if we have some permutation? Right, let's say, just for demonstration, this seems a little abstract, so just for demonstration, let's say we have the group G equals to, it just has 3 elements, G1, G2, G3. Okay. Again, it's not the same group we're talking about, we're just doing an example here. Right? So how would we show that, let's say, and I tell you that sigma equals to, I don't know, is some permutation of G. I maybe call it sigma of G. If I say sigma of G is a permutation of G, then it means that sigma is supposed to be some rearrangement of the elements G1, G2, G3. Okay? But for the rearrangement to really be a permutation of G, one is the elements being rearranged better be elements of G. So for example, if we have A, B, C as the permutation, well, so long as A does not, if let's say A is not equal to anything from the group, it's A does not equal to G1, G2, or G3, then sigma of G cannot be a permutation of G, because it's not even permuting elements of the group. And the other thing is, for you to be a permutation of the group, well, for sigma g to be a permutation of the group, it has to permute every single element. So for example, if sigma of g was just, let's say, AB, that is just A and B, a permutation of two elements, it can't be permuting the group because the group has three elements, not two. The other thing is that if you're really a permutation of the group, then you can't repeat elements. So for example, G1, G1, G2 is not a permutation of the group because we've repeated elements. Repetition is not allowed. The group is a set, and the set has elements written only once. They're not being repeated here. So this gives us a tactic for showing that, for determining whether GIG, whether this G, if you get the group G left multiplied by GI, well, that's just GI times G1, GI times G2, GI times G3, all the way to GI times Gn. Well, we're trying to check whether GI times G is a permutation. Again, bear with me for the moment about why we're doing this, but this will connect to a strategy of proving, in fact, that G is isomorphic to some subgroup of the symmetric group. Okay, so we're looking at GIG, okay, and we said that that's just the same as GI times G1, GI multiplied by G2, the elements of the group, and so on and so forth. All right, GI multiplied by Gn. All right, so we're saying that we want to prove that this is actually a permutation. So the first thing to do is, we need to check that each element in this thing that we're trying to see if it's a permutation, we need to first of all check that every element is an element of G, and we already said that. Since GI and G1 are both elements of the group, it means that GI times G1 must be an element of the group because the group is closed. So every element in here is an element of the group. We already know that. Okay. The other thing we need to check is that there is no repetition. That is, it can't be the case that, let's say, GI multiplied by some element in the group, GJ, equals to GI multiplied by some other element, GK, where J does not equal to K. Right? Because if this is true, right, if this is true, then it would mean that GI multiplied by GJ, basically that means that you multiply GI by some element GJ, right? Maybe you went down here, you multiplied GI by some element GJ, right? So, some element somewhere in GIG, and then you again multiply GI by some element GK, and you got the same answer. So what that would mean would be that we have two different elements of this set GIG. I mean, we have two elements that are the same, and if that's true, well, we can't have a permutation because we have some element repeated. We said that if you have a permutation, then elements are not repeated. The elements are all considered to be distinct. So let's check. Can GI times GJ equals to GI times GK, where J does not equal to K? Well, let's suppose that that's true. Let's suppose that GI times GJ equals to GI times GK. Well, since we're dealing with a group, elements have inverses. So GI has an inverse. So if we multiply both the equation by GI inverse to the left, we have GI inverse times GI GJ equals to GI inverse times GI GK. Okay. Now, GI inverse times GI just gives us 1. GI inverse times GI gives us 1 again. So we see that GJ equals to GK. Okay. So what this is telling us is that the only way, which obviously means that J equals to K, that is, really we're dealing with the same element here. Okay, so what this is telling us is that every single element GI times G1, GI times G2, GI times G3, GJ times GI times GJ, every single element here is distinct. Okay, so that satisfies the other property of something to be a permutation. One is, well, every element, as we proved, for every element is an element of the group. We've also proved that the elements are distinct because we've seen here that there is no way they cannot be distinct. That is, we started by assuming that, okay, suppose that Gj is different from Gk. Right? Then this calculation would tell you that Gj equals to Gk, which is a contradiction because we assume that Gj does not equal to Gk. So what this tells you that it makes no sense for any two elements in Gij to be different. So to be the same, that is, they're all different. Okay? And then the natural question remains, how many elements do we have here? Right? How would we figure that out? Well, we have Gi multiplied by G1, so that's one element. Gi multiplied by G2, that's two elements. And Gi multiplied by G3 would give us third element. They've actually been indexed for us by 1, by 2, all the way up to n. So we have n elements, which is exactly the same number of elements in the group G. So what that tells us here is that G of Gij is actually a permutation, a rearrangement of the elements of the group. So in general, what we're saying is, look, if you give me any group G, okay, and you're telling me the group is finite, it has the elements G1, G2 up to Gn, okay, if I pick any element in this group, let's say G1 and then multiplied by G, this is a permutation. It's just a rearrangement of this group. It doesn't give us any new information, it just rearranges everything. G2 applied to G is just, it just mixes up the order in which these things are written. It's a permutation. G3 multiplied by G, this is also just a permutation. It doesn't really change anything, and so that means that in general Gij, right, that's what we're saying is Gij, where Gi is an element of the group, is a permutation of the group. Okay, so natural question is fine, we agree that Gij is a permutation, but why is that important? How does that help us to achieve our goal? Because our goal is to show that every finite group is isomorphic to some subgroup of the symmetric group. Right? So how is that going to help us here? Well, first thing is, once we have this information, we can actually create a homomorphism, right, from the group G. Let's now create a homomorphism phi from the group G to the group SG. That is the symmetric group on the number of elements that are in the group. Okay, so what homomorphism are we going to create? First of all, I guess first question is, we know the elements of G. The elements of G are just elements of the form G1, G2, blah blah blah, up to Gn. Okay, we know that. What are the elements of SG, the symmetric group on G elements? Well, these are just going to be permutations. Right? So let's say permutations sigma 1, sigma 2, blah blah blah. Right? That's all they are, sigma n. Right? That's what the symmetric group is, filled with permutations. So sigma 1 is going to be some rearrangement of G elements, of cardinality of G elements. Sigma 2 is going to be some rearrangement of these G elements. Sigma n is going to be some rearrangement of the G elements. So what we need to do is to somehow create a function that connects these elements of G with these elements of the symmetric group. How are we going to do that is the question. Well, let's get phi. It's going to take any element of the group. It's going to take, let's say, Gi. And what it's going to do is it's going to send Gi to the permutation sigma Gi, or maybe what we're going to call it instead is, since we've already established some nice notation here, we're going to send it to the permutation. Oh wow, okay, there's a pen. To the permutation GIG. Okay, so again, GIG can actually be viewed as a function. Maybe that's another thing we forgot to mention here. So this was GIG, right? Is there any place where it was written a much cleaner way? Actually, this works. Sure. Let's write it down again to be really clear. So GIG is just, as we said before, is going to be G1G, G2G, G3G, all the way up till GN. What's happening? All right. Big mistake. Let's erase all of this. So actually, let's just. Right. Too lazy to erase everything. So we have GIG. That's just, we said, is the same as multiplying GI by every element of the group, by G1, GI by G2, blah blah blah, GI by Gn. So you see, we could think of GIG, we said it's a permutation. In particular, we could think of GIG as a function. And so, well, if GIG is a function, you might ask, well, what are the inputs? Well, the inputs of GIG are elements of G. For instance, what do you think GIG of, this is a function, it takes in inputs, right? So if I give you a function f, you ask what are the inputs? X, so we write as f of x. X is the value you plug into f and it gives you an answer. Here's the same thing, we have GIG. Well, what do we plug into GIG? Make a wild guess. You find out it's a guess that makes sense is G. Is the elements that you plug into GIG, the permutation GIG, are just going to be group elements of the group. So let's, for example, think of what's GIG of 1. GIG of G1. Well, so we're saying we have GIG and we're wondering what does GIG, this permutation, do to the element G1. So we are going to define it to be GIG takes the element G1 and gives the element GI1. GIG takes the element G2 and gives you the element GI2. GIG2. Right, so for example, GIG gets the element G1 and gives you back the element gives you the element GI multiplied by G1. That is just the answer when you multiply GI by G1. GIG applied to GJ. Right. You could think of GI as acting on GJ. GI acts on GJ by giving you GI GJ. Right. And that's kind of the principle. GIG is going to act on, let's say, G3. What do you think that's going to give you? GI times G3, where this times is just the operation in the group. Okay, so we now have a concept of, we can also view this GIG as a function. It's a permutation, in particular it's a function. And it takes G1 and gives you G1 times GI times G1. It takes G2, gives you GI times G2. Takes Gn, gives you GI times Gn. And so on and so forth. So we're now back to this part, right? Remember our strategy was, in order to prove, right, what are we trying to prove again? What's the goal? We're trying to prove that G is isomorphic to some subgroup H of the symmetric group, right? Some symmetric group. Let's say maybe, in this case, we're going to say the symmetric group on G elements, right? So, and the way what we're doing right now is we are trying to create a homomorphism between G and the symmetric group on G elements. That's the first thing we're trying to do. And then we'll see how this leads us to an isomorphism later. Okay, so phi takes in GI, and since it's a function, this is the domain, this is the range. So it's going to take in the element GI, and then what it's going to do is it's going to give us GIG of whatever. Okay, let's say it takes in the element GJ. We don't want to use the same symbol here. Well, actually, why not? So phi is going to take in the element gi and give us the permutation gig. Okay, so all it's going to do, it's going to give us this permutation, and we said this is also actually a function. Okay, well, I guess basic question is, first of all, is this a function? How do you prove that something is a function? Well, one key thing is that there have to be inputs, there have to be outputs. Well, the inputs are g, the outputs are the outputs of this phi, of this thing that we think is a function. The outputs are things of the form gig, which are basically, these actually turn out to be permutations on g elements. Okay, and so they actually turn out to be functions. So it's a function that takes in a group element and gives you out another function, or a permutation, which is just a function. So first of all, we need to check that this is a function. Well, first let's see if that's true. Well, also, to be a function, you can't be one to many. So gi cannot give us two different values. Right? But we see that this is not possible, because whatever gi I plug in, I'm going to get gig. Right? There's no way I'm going to plug in phi of gi again is going to give me, let's say, gkg, where k does not equal to I, because if that happens, I'm saying that gi equals to gk, basically. Because we said before, the only way two permutations can be different, the only way, okay, well, maybe not that way, but the idea is gi is just gi. Gi can't be some other element of the group, because the group is a set and every element is not repeated. I don't know if that's convincing to you or not. We're trying to show that this function phi can't be one to many. That is, it can't map one value to many different values. So that is, if we plug in gi into it, it can only give us gig. It can't end up giving us, let's say, gkg for some gk that doesn't equal to gi. So this is just true by the definition of how we've done things, right? Because by definition, if we have gk that's different from gi, then phi of gk is what's equal to gkg. Okay, so it can't be one to many. And by the way, another thing, actually maybe that's something we'll prove later. So I guess actually the way to prove this would be to show that gig, right, we need to show that gig then can never equal to gkg, right, where if I does not equal to k. Okay, if we show this, then we would have shown that right, actually that is precisely what we need to show. So we need to show that we're saying I cannot equal to k, so we need to show that gig does not equal to gkg. Okay, if gi and gk are different elements, because that would have shown us that gi cannot somehow turn out to be the same thing as gig and gkg for some other gkg. So how do we prove this? Well, the only way that gig can equal to gkg is if these two permutations do the same thing to every element. That is, if you get gig and you apply it to some element of our group, let's call it gm, right? That's how we've written elements of our group. That has to be equal to, right? We're trying to prove that let's suppose that they're equal, that gig times gm equals to gkg, right? The function applied to gm. Well, as we saw before, what's gig times gm? Well, that's just gi times gm. Okay, what's gkg times gm? That's just gk times gm, right? Now gm is an element of a group, so it means we can multiply to the right by the inverse of gm. So now we have gi times gm multiplied by gm inverse equals to gk times gm multiplied by gm inverse. This gives us that gi equals to gk. So you see, what we're saying here is that if GIG and GKG are the same permutation, then they must send every element GM to the same place because they're the same permutation. But if that's the case, then GI times GM must equals to GK times GM, right? By definition of what the permutation does. The permutation GIG takes the element GM to GI times GM, right? That was how we defined it before. And the same thing with GKG, takes the element GM to GK times GM. So, and that will give us this. Multiplying by inverse, we'll see that GI equals to GK. In other words, the only time that GIG can ever equal to GKG is if GI equals to GK. So that means then that what we're trying to prove before here, that this phi is actually a function. That is, it gets an element GI and never gives you two different elements. That is, phi of GI, phi of G sub I equals to GIG. And this phi of GI cannot ever equal to anything else. Because if it were equal to GKG, then we'd be saying GKG equals to GIG, which would mean that GI equals to GK, right? So this is basically proves to us that phi never sends any element to more than one element. It's not one to many. It's it only has, each element has only one output, and that convinces that phi is a function. All right. So we've just, again, we're trying to find a homomorphism phi from G to the symmetric group on G elements. And so far we've just shown that the function phi that takes in GI and gives us GIG, well, we've first of all shown that this phi is a function. That's good. Now we need to show that it's a homomorphism. How do we prove that a function is a homomorphism? We prove that by taking two elements. Let's take GI and GJ. Those are both, let's say those are elements of our group G. That must be equal to phi of GI times phi of GJ. That is exactly what it would mean for phi to be a homomorphism from our definition of what a homomorphism is. So then, we need most, well, maybe not. Okay, so let's do this part separately. So let me write it here. When I prove that phi of GI, right, phi of GI times GJ equals to phi of GI, times phi of GJ. So that's what my pen is the pen is misbehaving, but yeah, that's what it's supposed to equal to. All right. So we need to prove that the left hand side equals to the right hand side. Well, question: what is phi of, all right, what is phi of GI times GJ is the question. Well, from our definition here, phi of GI is GI times J. So that means that phi of GI times GJ will just be the same as, we're saying that phi of anything, phi applied to anything, any element of the group, gives us that element of the group multiplied by G. So what we're saying that this is the same as GI times GJ multiplied by the group itself. So it's this permutation, GIGJ, this is J, let's erase that. Alright, so this is J right here. Yeah. So gi is an element of the group. Gj is an element of the group. When you multiply them, you still get an element of the group. So we're considering the permutation on G that's created by multiplying every group element by gi gj. Okay? So that's what phi of gi gj equals to. Remember when I proved that phi of gi gj equals to this. So now let's check phi of gi instead. Another eraser again. All right, another erasure. So what's phi of gi times phi of gj? Well, from again the same idea is this would be the same as this part here would give us gi times g multiplied by gj times g. Right? This part would just give us gj multiplied by g. Right? Remember again the definition of the function is of a function here is that it takes in an element and gives you that element multiplied by the big G. Okay. So our task is now to prove, since we don't prove that this equals to this, our task is now to prove that this thing equals to this thing. Well, okay. So how can we do that? Well, remember that this gj times big G is still a function. And this is also a function. It's just this is a composition of functions, because this is a function and that's a function. So we just need to show that this function is the same as that function. Well, functions take in stuff. Remember we said before that gig is a permutation that takes in some element gk of the group and gives us back gk. Okay, so if this function, which is a permutation, but if this permutation is a function, if this function really equals to this function, then it must be true that what we really need to show is this. See if you agree with this, that gi times gj g, if you get that and you apply it, if you get this permutation of function and apply it to gk, we want to prove that that is equal to, okay, we're running out of space. Okay, let's write this down here. Okay, let's hope it's not too confusing. So right, so we're saying that gi times gj multiplied by big G, right, this permutation here, when you apply it to gk, the answer you get is the same as if, that's what we're trying to prove, is if you get the permutation gig, compose it with the permutation gjg, and then but this permutation is being applied, this composition is being applied on the element gk. If the left hand side equals to the right hand side, then it means that this function here is the same as that function there. Alright, so it's very hairy, but yeah, let's work it out. Well, from our definition, from our definition, we saw before here that gig, the permutation gig applied to gk is just gi times gk. Okay, so then what do you think gigj multiplied by g applied to gk, this left hand side, is going to be? What do you think that's going to be? Well, that's going to be exactly what you think it is. It's gi times gj multiplied by gk. Gi, gj, gk. Okay. What about the right hand side? Would have gi times g multiplied by, composed with gig of gk, okay, which is just the same as you apply this function to gk first and then this function to the answer. So gi then times g, we have gi times g of whatever this thing is. Gig times gk is just gk. Okay. And what's gig times gik? No, this is still an element of g. Well, that's just gi. This was gj actually. This was gj, yeah. Gi, gj, gk. So what do you notice? This equals to that, which means that this whole thing equals to that whole thing, which means that this function equals to that function, which in turn means that phi of gig, which is that function, equals to phi of gi times phi of gj. So that tells us then that phi of gij equals to phi of gi times phi of gj, which is what we're trying to prove here, that phi is a homomorphism. Okay, so again, this was a lot really involved. So what have we done so far? We've looked at phi. Okay, we've created a function phi from g to the symmetric group on g elements. Okay, we've defined the function to be the following. It takes in a group element, and then what it gives you is the permutation that that group element induces on G. Okay, that's what we defined phi to be, and we've just proved that phi is a homomorphism. Phi is a homomorphism. Okay. If phi is a homomorphism, what does that mean? Well, first of all, it means that phi of G, okay, all right, so this means that phi of G is, if phi is a homomorphism and G is a group, phi of G is a group. We proved that in the prerequisites. Phi of G is a group. Okay? So, now all we need to show is that, notice, if we can show that, okay, we run completely out of space here. Do we have any more space at the bottom? Yeah, sure. Actually, we do. All right. So, we showed over here that we've shown that phi from G to the symmetric group on G elements, that is, if just a permutation of the elements G1, G2, G to Gn, we've shown that this phi is a homomorphism. Okay, that's written correctly. Phi is a homomorphism. Okay, so that means that phi of G is a group. We've just established that. I mean, that's what we proved in the prerequisites for this theorem. So phi of G is a group. So what does this mean? If we can show, right? If we can show that the group G is isomorphic to phi of G, then it would be done, because we already know that phi of G, if phi of G is a group and phi of G is remember, phi of G is the image of G, so it is a set of permutations on the elements of G. What that means is that phi of G is really a subgroup of the symmetric group on G elements. Okay, so we've just shown that G is isomorphic to phi of G. Okay, so I mean, if we can show this, then really what we'd be saying is that G is isomorphic to phi of G, which is a subgroup of the symmetric group on G, which would mean that G is itself isomorphic to a subgroup of the symmetric group, and would be done. That would be Cayley's theorem. So this is what we're left to prove right here, that G is isomorphic to phi of G, the image of G, image of phi. That's what's called phi of G. All right. So how do we show that something is an isomorphism? One, we need to show that it is a homomorphism. Okay. And then two, we need to show that it's a bijection. Because remember, an isomorphism is a bijective homomorphism, or a homomorphism which is a bijection. Well, is phi a homomorphism? Yes, we just proved that. That's what we proved right here. We proved that indeed phi of gi times gj equals to phi of gi times phi of gj. Okay, we proved that. So phi is a homomorphism already. Okay, phi is homo. Alright, put that there. Phi is a homomorphism. All we need to prove is that phi is a bijection. Okay, so how do you prove that something is a bijection? You prove that it's injective and surjective. Okay, is phi injective? That just means one-to-one. Well, to prove that phi is injective, all we need to check is, is it surjective? Okay, let's start with surjective. Seems to be easy actually. Move from the simple to the complex. Right? Remember, we're thinking about phi from G to phi of G now, right? So we're thinking about G, the map from G to the image of G. Well, is that surjective? Yes, because phi of G is the image. And what's the image? Everything that, all the elements that G maps to. Okay, so by definition, since phi of G is the image of phi, it's surjective. So we prove surjectivity. Phi is surjective. Okay, phi is surjective. That's done. All we need to prove is that phi is injective. Okay, how do you prove that it's injective? We just prove that there are many ways, but we just prove that if you get two elements, G1 and G2, of G, then the only way that phi of G1 can ever equal phi of G2 is if G1 equals to G2. If we prove this, then we'll have shown that it can't be the case that two different elements of G give you map to the same thing in phi of G, and that would mean that it's injective. So let's prove that. So let's take G1 and G2 elements of the group and show that phi of G1 equals to phi of G2 necessarily means that G1 equals to G2. Alright. Okay, now we've completely run out of space here. Oh, wait a second, have we? Okay, yeah, we have. So let's just erase and create some space. So we'll give you time to internalize the concepts, or at least take it in, because that's been pretty involved. Yes. All right. So let's work it out. Let's suppose that G1 and G2 are actually elements of G. Okay. Then suppose that phi of G1 equals to phi of G2. All right. So we showed that we just need to conclude from here that G1 equals to G2, which would mean that phi must be injective. Well, how do we do this? Well, one way to do it is just check G1. What's phi of G1? That's G1G. Yes? By definition of what phi is. Remember we said that phi of G equals to G big G, the permutation that G induces on the group G. And phi of G2 is just G2G. Alright. We know that. So, and remember we proved before that, actually we already proved this. We proved that if G1G equals to G2G, then G1 equals to G2. Now, we actually proved it early on, but maybe just as a demonstration. Remember that G1G is a function, and G2G is a function. So what that means is that the way to prove that the two functions are equal is to show that if you apply them to the same element, you get the same element back. Right? If they're equal, that's what it means. It means that G1G times GK times G1G applied to G2G applied to GK, that these two things, well, I mean, if G1G equals to G2G, then G1G applied to GK must equal to G2G applied to GK. But what is G1G applied to GK? Well, that's just G1GK. And what's G2G applied to GK? Well, that's just G2GK. Well, GK is an element of the group. That means it has an inverse. So if we multiply both sides to the right by GK inverse, right, and then we multiply both sides, right, by GK inverse. Actually, the parenthesis should have gone here instead. All right, let's fix that. If we perform this multiplication, the end result is that, I mean, the GKs are going to cancel to just 1, and so we have G1 equals to G2. So what have we just proved? If phi of G1 equals to phi of G2, then G1 must equal to G2. This means that phi is injective. Okay, so this is good news, because what this means is we've gotten phi. Where did I write it? Where did we write it? Okay, we've gotten phi. Oh man, all right. Okay, we just run out of space officially. All right, we have some space over here, so we're gonna make use of that. All right, so that's right. So we're gonna make use of some of that space. So right there. So we've just proved that we've gotten phi from G to the symmetric group on G elements. Okay. We showed that phi is a homomorphism. Phi is homomorphism. Then we showed that phi from G to phi of G is 1. We know phi is already a homomorphism. We know that phi is injective. We just proved that. We know that phi is surjective. So phi then is a bijective homomorphism, which means that phi is an isomorphism, which means that G is isomorphic to phi of G. But we proved that phi of G is a group, which means that, and phi of G is a subset of S of G, the symmetric group on G elements. What that means is that phi of G is really a subgroup of the symmetric group on G elements. So we've just proved that G is isomorphic to a subgroup of the symmetric group, which is exactly what Cayley's theorem wants us to prove. Alright, that was really hairy, a lot involved, so I recommend maybe taking a look at the video a couple of times to make sure the logic connects. But it's a really powerful theorem, as I was mentioning, because what it's telling you is that among many things, okay, where was it? Where was it? Okay, good. We don't want to lose this. Okay, so among many things, what it's telling us here is that, look, anytime you have a finite group, the finite group may look really weird. It could be matrices, it could be rotations, it may look very different, it may be complex numbers, but really whenever you have a finite group, it's really the symmetric group in disguise. So if you study the symmetric group, you're really studying all the groups. A really powerful and deep concept. All right, thanks for listening to this, and bye.